So this work is joint work with me between my students and postdocs over the years, most of them, and some of them actually I did during my postdoc. Like I mentioned, I'm from Texas. So this is my current group. So I have 4 students working on UQ inverse problems and 2 students working on high order finite element methods, and both postdoc working on machine learning and inverse problems. And our group actually have been funded by government agency, industries, and also international collaboration, like for example Portugal and Mexico. So let me start with showing you the what kind of application or what kind of problem that actually we are working on. The one that I'm showing you up here is the fourth UQ problem, where you actually design, right? You are design a wind or the turbine blades to satisfy some conditions. And then you send it to the industry, to the manufacturers. And as soon as the manufacturer do the manufacturing process, it gives you a lot of variation, right, compared to the original designs. Right? I'm going to show you that in a second. The question is that the variation in the manufacturers, how does it affect the stability and many conditions of the original design, right? So what I'm showing you here is just one passage, right? A flow over a passage here of turbine blades. What we want to do here is that we want to model the variations due to the manufacturing process by random variables. And we want to do simulation to see how these random variations actually affect the sum of designs. And we want to do so under very large scale simulations, right? So that's the first application. The second application is the one I'm showing you here. Here we do a simulation over electromagnetic scattering over a whole aircraft here, as you can see. And this is the inverse problem where you send a radar, right? You send a radar to like the border of your country, right? And then you can measure reflected waves. The question is, from these limited number of measurements, can you actually make inference on the shape of the objects, right? Is it an aircraft or a rocket from the neighbor? Let's say you stay to a very sensitive neighbor, right? So that's a problem that of interest, and this problem is challenging for many reasons. For example, the data are limited. We don't have a lot of data. We do, but the limited informations, and more importantly, the data has noise, right? Come with it, because any devices, right, come with some tolerance, and we know, right? That's for sure, right? There's no way that a device can measure things exactly, because we are human, right? By human nature, we cannot do things perfectly. And we want to solve the inverse problems, this kind of inverse problem in a very large scale setting, right, where we discretize the PDEs. You heard from the previous talk from a local professor here, where we do large scale discretization when we have a lot of degree of freedoms. Can we actually do an inverse problem, right, in such a large setting? I'm going to show you how we do it on the supercomputers in a second. And the third application that I have been working on is earthquakes, right, and in particular imaging of the earth. So what I'm showing you in the middle here is a simulation of Japan earthquake here, and if you can see, I'm not sure whether you can see, there's on the continent here, we do a global earthquakes, right? This is on the global scales on a few 100,000 processors, cores, right? I'm going to show you in a second. And this problem is the same type of features, right? The fourth problem where you know the structure of the earth, right? And if you know if you have earthquakes and if you know the structure of the earth, you can do simulation forward in time, right? To see where the earthquake is actually moving, right? To any places, and what is the magnitude of the earthquakes. The inverse problem is actually harder, and that's what we have to deal with, right? We have the measurement of the earth movements, right? The question is that how you image the interior of the earth, the density of the rock structures of the earth, and that's what we are interested in. And again, randoms in the measurements, inadequacy of mathematical model. Here we use linear elasticity as modeling the earthquake similar propagations. And we want to do so in a very large scale, 10 to the 9 billion degree of freedom. I'm going to show you in a second. So these are the type of problem that I'm interested in. And let me actually tell you what are the challenges when we deal with these problems. Thanks to the previous talk, then you can see that we have a similar structure here, right? The only difference is that now I'm looking the things in the statistical setting, right, Bayesian setting. If you don't know about Bayesian, don't worry about that, right? I hope that the lecture from the last speaker is clear enough, right? There's there's he called it fidelity, or I forgot what he called it, but we typically call it data misfit, right? Where you have an observation here. This is the real observation when you measure from your devices, right? And GU is what we call a parameter to forward map, right? U is a parameter that we want to invert for example, the structure of the Earth or the shape of the aircraft or some objects. And G is the map from the parameters to observation, and you do so through solving the PDEs, right? You see that U is a parameter in your PDEs. For each parameter, you assume that you can solve for the state, which is W here, right? And when you have a W, you can have a map from the W, right, to the observations. That's what it means, right? In order to evaluate this map, you have to solve PDEs, and that's actually the challenge. And of course, right, we know that no matter how many data you have, this problem is ill-posed. You have to equip with the regularization, right? Or, if you are Bayesian guy, this is nothing more than the negative log of the prior. Okay, so we have three key players in this inverse problem, right? The first one is the data, right? I mean, we want to solve the problem in the context of high-dimensional data. In particular, it's very relevant for the last two applications that I show you, earthquakes and electromagnetic. Earthquakes in the U.S., we have about 500 seismometers. Seismometer is the devices to measure the movement of the Earth. So every millisecond we measure the movement of the Earth. So every minute we have terabyte data and so on and so forth, right? The question is that when can we actually use the historical data, right, to actually image the Earth? So when you have the high-dimensional data, you know that we have a problem with the output and input, right? So some of you, if you don't work with the large-scale problem, then there's no problem. But if you work with high-performance computing, you know that nowadays, right, current and future in computing infrastructures, not compute bout, right? You already saw from the previous talk where you have million cores, so computing is no problem, but you have memory bounds. That's a problem for any computers. And here, therefore, the high-dimensional data become problematic, not only for the forward solves, right? This is the forward problem, but also adjoints. And in our work, we use adjoint a lot. And this problem not only showing up in the forward, but also adjoints. And this can make the slow down computation if the computing structure actually memory bound. Okay, the second problem is the high-dimensional state, right? You have a PDEs, which is, this is just a model. You discretize with any method, finite difference, finite volume, or finite elements. When you discretize, in order to resolve the physics, you have to discretize in the finite mesh in order to get accurate solution, right? So this can become very expensive. And if you work with the numerical PDEs, you say, who cares, no problem, right? I mean, how expensive, I still can do it. Unfortunately, in a Bayesian or inverse problem, that's not the case because you have to solve the forward problem many times, right? And even you said, oh, I have a day to solve my forward problem, but how about if I need to solve my forward problem million times, right? That means million days. That that no longer become feasible. And I'm going to show you in a second some of the applications. And this actually show up in the MCMC Markov chain Monte Carlo approach for the statistical inverse problem where you do sampling, right? Each sample you need to solve a PDEs. Okay. And another key problem for inverse setting is the parameters. So the parameter typically, from the previous talk, you have a control, or you have initial condition, things like that, or the parameter. Like let's say this one is a log conductivity, right? You have to discretize because this guy actually lives in some function space. You have to also discretize not only W, which is the state, but also U, which is the parameters. As soon as you discretize, right, and if you refine the mesh, you have more and more parameters. And that's the curse of dimensionality from the first talk, right? The cost of dimensionality says that as long as you increase the number of parameters, the cost actually increase exponentially. That's what it means in terms of in the context of statistical approaches. Okay, so these are three problem or three challenges that I have been dealing with. So today I'm gonna do very quickly on high dimensional, how we deal with high dimensional state space. Quickly on high-dimensional parameter space. Most of the time, right, the rest of the time I'm actually spend talking about a randomized technique to deal with data, especially because this workshop is on data, so I'm going to spend time describing a method that we actually come up with and show you rigorously how actually it works for high-dimensional data. And I'm going to conclude and then some future work at the end. Okay, so back to this CFD problem, computational fluid dynamics. This is the equations, Euler equations. If you know, otherwise don't worry about that. So in order to solve this problem, remember that we have many, right, millions of shapes of the cascade. Actually, we actually got the real data from the UTC company in the US, actually generally make it on these shape of the turbine blades, right? And we want to do simulation for each turbine. We want to solve a CFD simulation for each turbine, and then we do calculation of some quantitative interest. For us, we're going to compute some stability, right? So we have millions of the shapes. So that means we have a million simulation of the CFD code, and each of them actually can be, it depends, hours or weeks, and that become infeasible. So what we did here was to do a reducible model, right? So something similar to some of the talk before. I'm not going to go into detail, right? Just show you the idea. So we do model reduction on very expensive CFD code, and here we go, right? We can save days and weeks, but with only a few reduce, right? The capital X from the previous talk, right? Reduced states. This is the result from the reduced simulation. This is the result for the full simulations. And you see this is the shape of the blade actually changing, right? Randomly due to the manufacturing process. And our reduced model can capture the full model pretty well from statistical point of view, right? So we have the detail on not only the eyeball, where actually we compute the error, but I don't have time to show it to you here. Just to give you an idea, right? For this type of application, one way to do it is to do reducible model, like I just said. Another way to deal with high dimensional state. This is high dimensional state, right? Where it's expensive to solve PDEs. Another one to do is for this one is the inverse problem, right? This is the original. This is you can think about this is the thermal fin, and this is the conductivities, and this is what we want to invert for, and this is where we do the measurements. And if you do the standard, inverse problems, deterministic way, right, or you do the map pointing statistical way, this is what you get, right? Of course, it's intuitively good, right? Because why? You should be able to recover things close to the measurement, but far away from the measurement you cannot recover, right? If you look at that, then you spend a lot of time doing inverse problem for the whole thing, but what you get here actually is not useful. Why should I spend time doing here, right? So the idea is actually how about I throw away part that actually not useful or have a lot of uncertainty, have a lot of errors. So what we did is actually we solve a deterministic inverse problems, right, which is this one, and we estimate the uncertainty and we throw away part of the region where the uncertainty is actually large. And then we do MC sampling, right? Statistical inverse problem on the truncated domain. And this saves not only the states, right? Now we do a smaller domain, so we can solve faster, but also we can actually reduce the number of parameters, right? Because we don't invert for these parameters. And as you know, right, one of the reasons why the inverse problem is imposed is that you have limited data and you have too many parameters, right? So this one actually can cut down the number of parameters, right, for you. Okay, so this is a 3D thing that you can see here. Again, we just do a very prototype test problem here where these are two lobes. You can see like two oil reservoir, right? And you have measurement here, let's say, right? And this is the inverse problem that you get for the full domain, right? Of course, you can recover. This one is okay. But what we did is, we're going to do inverse problem. We solve a deterministic inverse problem. We estimate uncertainty and we throw away the region where the uncertainty is high. And then we do reconstruction, right? Statistically in construction. And you see that, on the smaller domain, because you have less parameters, you can recover even better than the original one. Okay, so these are two method that I wanted to share with you on how we deal with the high dimensional state space. Now next, let me move to high dimensional parameter space. In this front, we do a lot of developments, in particular macro chain Monte Carlo method. We have developed different type macro chain Monte Carlo method. In particular, what we did is actually we don't do the traditional macro chain Monte Carlo method where you don't use the information from the model, right? If you look at the macro chain, traditional macro chain is like machine learning. You just use the evaluation of the code, the data, right? But you don't actually explore the structure of the problem. So what we actually develop is actually we use gradient enhanced, right? We use gradient Hessian, even we use triple derivative, third order tensor in order to enhance the mixins of the MCMC. So for those that actually you haven't heard about Markov chain Monte Carlo, don't worry about that, right? The key idea is that we want to take advantage of the structure, exploit the structure, the problem through the derivative, right? And again, we can do so efficiently by adjoint technique, right? Without adjoint, you cannot do that efficiently. And by using that, we actually can make the MC fast and accurate. Okay, I'm not going to show that, just tell you the idea. The second approach is actually quite orthogonal to the previous ones, right? Is we move away from MCMC. We actually borrow technique from data assimilations where particle approaches, right? So instead of doing MCMC, we start from the sample of the prior, and we try to somehow move these samples to the posteriors, right? Because at the end of the day, for the statistical inverse problem, at the end of the day, what you wanted to get sample from the posteriors, right? And we do so, you can do MCMC or you can do many methods. What we do here is that we start from the prior, and I'm going to show you two techniques, right? One of them is optimal transport. We use discrete Monte Cantor-Ravik approach where we transport the particle from the prior to posteriors. And second one, we're going to use a gradient enhanced ensemble Kalman filter. So we convert the inverse problem into the data assimilation problem, and then we use the ensemble Kalman filter. But we don't stop at that point, right? We actually use the gradient to actually make the ensemble Kalman filter faster and more accurate. I'm going to show you in a second. The third thing that we have been doing is on reducer model, or you have seen many talk, and that's actually quite natural because for this type of problem without reduction of something, you'll never be able to solve practical problems, right? So we're going to show you a few reducer model approaches that we actually developed over the years. And then we're also looking at the optimal experimental design, right? This problem is actually a little bit different on the big data point of view. The question is, where do we actually do the neck measurements to get the most information about of your system? In particular, where do I put the neck measurement in order to get the best reconstruction of the inverse problem? For example, the image of the Earth or the shape of the objects, right? So this is well-known optimal experimental design problems, and we develop fast algorithm, but I'm not going to show it to you here. Just tell you what I'm doing. And actually, this is actually interesting. We have been working on developing a new technique, right? Not Bayesian. So this is a new technique. Bayesians, what Bayesian does, right? If you do inverse problem, you have a misfit or a likelihood, and you have the prior or the regularization, right? And then the reason you put the regularization is to make the inverse problem well posed. The problem is that when you put the regularization, you also regularize everything, right? You regularize every parameters because you don't know where you should not, right? And in the ideal world, you don't want to regularize the direction of the parameter where it is informed by the data, no matter how limited the data you have or how big the data you have. But the data sees some important, right, or some reduced dimension of the parameters, right? And when you put the regularization of the prior, you don't want to pollute the well-informed or data-informed direction of the parameters. And we actually start from day one, step one, right? We start from measure theory. We develop a rigorous method to design a new statistical framework where whatever you start, give me a prior, I want to make sure that this framework makes sure that the prior will not touch the informed data directions. Again, I just tell you one other thing that we do. Of course, right? Everybody talk machine learning. I have a student working on machine learning technique for inverse problems. Okay, let me start with two things, right? The particle approach and reducer modeling, because I think it's interesting. Let me quickly show you. Like I said, right? I start from the prior. This is the distribution of the prior. This is the complicated posteriors. The question is that if I have a limited number of particles or sample from the prior, how do I move to the particle or the sample of the posteriors? And we do so by optimal transport. So we borrow the technique from the data assimilation where we actually do a annealing, right, or sequential approach, right? We, instead of going directly from the prior to posterior, which is using complicated, right, we move to many steps in between, right? We move the particle to a little bit something actually not very different from the previous one, and then move to the next something that is not very different from the previous one, and so on and so forth until we get to the posteriors. Of course, right, your question may be, oh, how do you know how many things in the middle, right? So of course we have an adaptive algorithm to do it. Again, I'm not going to show it to you here, but I'm just showing you a result. Right, we can talk offline more. For example, if you do a standard thing, important sampling or standard technique, you will not be able to, this is the posterior, right? You're not going to be able to do it well. But our method, right, by solving a linear optimization, right, it turns out that if you look at the Monte or optimal transport approach, if you look the original formulation by Monte, it's actually a nonlinear optimization. But if you look at the Kantorovich approach, it's actually linear, but it's a high-dimensional linear optimizations. So we took that one because it's linear. But it's, of course, it's a little bit more higher dimension, but that's the trade-off, right? If you want to go from non-linear to linear, you have to increase somehow, right? No free lunch. But it's easier for us to do so. And you see that we can capture the posterior multimodal, right? That's for us. For earthquakes simulations or inverse problem, this become important because we have a lot of multi-local minima. Okay, so another one that I want to share with you is the derivative enhanced ensemble common filters. So we have an inverse problem which has nothing to do with the data assimilation. Remember that from the previous talk, data assimilation, you have the data measurement in time, and you look at your prediction, and you look at the current data, and you see the mismatch, you correct, and you move on. Predict and correct, right? So we convert the inverse problem into a data assimilation problem, and then we can apply the ensemble common filter. But the idea is not new. What we do new here is, or a little bit new, is a derivative. We enhance the ensemble common filter with the derivative. And I'm going to show you a couple of results here. This is the choose solution, right? Or you can think this is like, or again, like a reservoir. We actually have the project with ExxonMobil, so we do something along that line. So this is ensemble common filter. If you don't do anything, then it will not converge. But if you do with a gradient descent with 55 steps, right? This is the fixed steps. This is what you get, right? You see something. This Newton 55 step, you get something. But here these are fixed. So what it shows that if you have a fixed step, it's not good. And if you do optimization, you never actually do a fixed step for optimization descent direction. You have to actually change during the time. So this is adaptive, right? Backtracking, if you will. So with the backtracking technique, right? Well, Newton method, you see one already good, and actually even 15 iteration, we only get almost the same thing at the exact solution. And this is some of the covariance. So that's actually done with my introduction to the two challenges, right? High dimensional state and high parameter state. And we show you actually the only two things that we have been doing so far over the years. Another thing that we're going to show you is actually response surface or machine learning, if you will. This one is an electromagnetic scattering problem where this is the shape, the exact shape of the sub-object. We don't have the exact one, of course. We have the measurement on this side, right? And we want to invert for this shape. And this shape is actually well known. If you do shape optimization, this is well known difficult because you have a convex and concave and then convex. And that's very hard to recover exactly. So what we do here, I'm going to show you with 24 shape parameters, and we run 1 million Markov chain Monte Carlo simulations. And the green or the blue one, actually the average, right? And you see that we can recover the front face very well again because we have the measurement here. But at the back, we do okay, right? But of course, we don't have the information because measurement is actually down here. The key point I want to show you here is that we develop an adaptive, non-stationary Gaussian process. The standard Gaussian process, again, like machine learning, it doesn't actually use information. We actually equip with Hessian informations to adaptively, right, to change the kernel of the Gaussian process, and that actually help us to improve the computation better. If you use the Gaussian process, you spend 33 hours, right, upfront cost to build the Gaussian process adaptively. But then this is the online cost is the one that we actually care about, right? If you do 1 million simulation for online using the Gaussian process, you take almost an hour. But if you use the original finite element model, you get, you need about 8,800 on 2 hours. That's too much, right? So that's where we can reduce the models. And here, before I actually show you the earthquake inverse problem, I'm going to show you the fourth, right, high order finite element code behind the inverse problems solvers. So this is DG, this continuous looking finite elements, and this explicit, this is strong scaling that I show you, and we scale, this is 7 years ago when we scale our code up to 262,000 processors back then on the Jaguar. Back then, this I think it was number one back then, I think. But now it's way behind the rest. In fact, it no longer exists. Titan actually, is actually replaced this one. So if you look at the parallel efficiency, we get 71% of parallel efficiency. And the beauty of high order methods is that if you increase the higher order, you get better accuracy, but of course you have a more number of degree of freedoms, but you get almost perfect parallel efficiency. The reason is that high order methods, right, force you to work locally a lot and you don't see communications. And that's where you get gain the parallel efficiency. And for us, right, wave propagation high order methods is important. And let me actually use that code, right, to do a similar inverse problem for the earthquakes here, right? So on the left is a synthetic. This is how I believe the earth structures look like, the density look like, right? And this is the measurements. It is the earthquakes, the black ones are the earthquake sources. And on the right-hand side is on the middle one is the recovery. Here we have 1.07 million parameters, right? If you do MCMC, and this scale is very expensive. We don't do MCMC. Well, we do, but I'm not going to show you. What I'm going to show you is not MCMC. It's what I'm going to show you a Gaussianization, and 633 million parameter field, right? W. 630 millions, but the U one actually have only about 1 million, right? And you see that, right? This is the final time, 1,000 seconds with 2,400 time step. Even on 64,000 processor, it takes a minute, right? So even with supercomputer, things become expensive if you want to do many. So what I'm going to show you is a map here, the deterministic inverse solution, if you wish, right? So you see that we can recover the North America very well, obviously, right? Because we put on the measurement here, but we don't do well up here because we don't have informations. And the right-hand side, we want to show you. I'm going to talk about that in a second. Here we use lowering approximation of the Hessians, right? Again, with Adjoint technique. And this is the spectrum, the Hessian. You see that at what we refine the mesh, the spectrum doesn't change, right? And that's important because what it shows that our lowering approximation method is not independent of the mesh refinements in the sense that the number of PD solved is constant, and that's important, right? And this is what I'm going to show you here is the prior uncertainty before you actually have an observation. You put down a prior the belief, right? How your Earth looks like. And this is your prior uncertainty when the data comes. This is the data. And this is actually the posterior or the update uncertainty. And you see that the update uncertainty actually much less around the North America region, right? This is the blue. And actually it's obvious, intuitively correct, right? Because that's what we should believe. Around the measurement, we have gained more information about reality. We should have less uncertainty. And this is our linearization approach, or Gaussianization. Basically, we fit posterior to the Gaussian distribution, and then we just this is the diagonal. What I plot is actually a diagonal of the covariance operator, which is the inverse of the Hessians, right? And we do so efficiently using the lowering approximation. And the reasons we can do lowering approximation of the Hessians because of the result that I'm about to show, right? The detail is not important, but we prove for many. Not many, right? 3 type applications where we prove that the Hessian is a compact operator, right? Many of you are mathematicians, right? So the compact operator has the spectrum decay to 0, right? That's by definition, right? And therefore, for such an operator, it makes sense to do lowering approximation. So this is a justification that for us to do lowering approximation in our 2 previous one, right? Remember that we do a non-adaptive Gaussian process with equipped with the Hessian, and this one, Gaussianization, we also need the Hessians, and we do so by using lowering approximation by randomized SVD and so on and so forth. The detail is not important, but it's just the idea, right? And we not only stop like that one, right? Because remember that we have everything is in infinite, right? The parameter is in infinite dimensions, the state is in infinite dimension. When we discretize the parameter, we discretize the state, we commit some error. The question how these errors affect the posteriors. And we actually characterize, we can measure, we can actually estimate the error between the posteriors, right? That discrete posterior and the original infinite dimensional posteriors. And this helps us to in the adaptation, which again I don't have time to show. The idea is that we actually also characterize the errors, right? From the numerical analysis point of view, error characterization is important. Okay, so let me move to the last part of the talk, which is the one that I want to focus on. The high-dimensional data. Remember that's why is high-dimensional, right? The question that we want to ask ourselves is, can we work with a low-dimensional subspace of the data, yet we want to reduce the number of PD solved, right? Remember that PD solve is the killer for our application because each PD is too expensive. We want to work on a smaller subsets of data. We want to reduce the number of PDs, but yet we want to obtain a reasonable solution, right? It sounds like too good to be true. And let me show you, actually, it can be done by machine learning, in particular random projections. Well, let me start. Okay, look at these two terms again. Again, this is the realization or the log of the negative log of the prior if you work with the statistical inverse problems. And this is the likelihood or the misfit or the fidelities from many imagings, right? What I will assume that's data Y observed is the dimension n, capital N, high dimensional data, right? Let me just look at the very simple one, right? One big long vectors. Of course, in practice, you have many of them, right, in tens. So what we're going to do is that we're going to introduce a random variables, right, with mean zero and covariance identity. Okay, so you have many of them out there, Gaussians, random marker, and many of them out there. In fact, we also have sparse random vector that actually satisfy the conditions. I'm going to show you in a second. So what I'm going to do is that I'm going to do a very simple thing. I'm going to insert, right? I'm going to randomize this one. So you see that this one is kind of identity here, right? If you don't see anything, it's identity. And you know the identity can be replaced by the expectation of RR transpose. So I put the RR transpose in here, and the expectation is the linear operator, so I can take it out, right? And what we got is now, it's like a stochastic optimization. The original problem is deterministic optimization problem, but now I have stochastic optimization when I randomize my data. Of course, when you see the stochastic optimization problem, you have many ways to solve it. What we do actually, very simple approach. When I see the expectation, I'm going to do Monte Carlo simulations, right? Because these I chose, right, or you choose. So you can draw sample from the R's, right? So let's say you draw little n samples. So you're going to approximate this expectation with n average, right, sample Monte Carlo. You don't do anything with the prior because you care about the data. And if I rewrite, right, I put all the random n of them, little n of them into columns of a matrix, right? This matrix have the dimension capital N and little n. Okay, so if little n much less than n, so I have reduced the data, right? But if you work with MCMC, you say, oh, what's good about it, right? Because you know MCMC converges very slowly. In fact, 1 over square root of n, right? So it looks like that you reduce the data, but you know, you make a lot of error here, all right? It turns out that is okay, right? That is okay. Let me show you why it is okay. And this is okay for two reasons. So the first reason is about concentration of measures, right? If you work with high-dimensional probability in high-dimensional space, right, there's a very active research. In fact, you know, there's a lot of books on concentration of measure. It turns out in high dimension tend to concentrate about in the little regions. Let me give you an example. If you look at the hypercube, we have been working with like 3-dimensional cube, 2-dimensional cube, and we may do 4-dimensional cube if we consider time. But in this kind of business, you have hypercube, right? It turns out that if you look at the hypercube and you take a very small shell at the boundary of the cube and you compute the volume of the shell with the high epsilon, okay? And you take the ratio of that little shell over the volume of the whole cube, right? And if you take the dimension, go to 0, the ratio converts to 1. Same thing with hypersphere. If you look at a very thin shell of the hypersphere, it turns out all the volume actually concentrated there, Okay, and that's a well-known phenomenon of concentration measure, and that's where we actually explore because of that fact. So let me start with the first ingredient, which is namely Johnson-Lindner-Strauss, and this is the well-known method in machine learning, right? In particular, computer science, where you want to do random projection, reduce the dimension of the data. The theorem says the following: let's take m high-dimensional vectors in Rn, capital N. It turns out that there exists a map P, right, from capital N to little n, right? And notice that the reduced dimension is independent of the original data dimension. This is the important one, right? It does not depend on the original dimensions. And then we can show that this map takes high-dimensional data space into a small-dimensional data space, yet you still preserve the distance, right, with some little error. And if you work with compressive sensing, this is actually well known the RIP, right? Not rest in peace. It's a restricted isometry property, right? And the random projection, and we're going to show you that actually the random projection can allow us to do so. It's amazing about this theorem, right? It's no matter how high dimensional data, you can reject into a low dimensional data, independent original data, and yet you commit some epsilon errors. Okay, that's the first ingredient. And the second ingredient is from the inverse problem. If you work with inverse problem, you never want to match this guy to 0, right? Because if you match this guy to 0, you match the noise. And that's a well-known problem. You don't get anything, right? Your solution looks bad. And one of the way to avoid this issue is the Morozov discrepancy principle. Morozov say the following: you solve until your solution, right? You get a solution, and then you measure the difference between your computer output and the exact data. And as soon as you make the error here is about the same, the level of the noise, you stop. And that's where you should stop, right? Then you don't overfit the noise. Okay, so notice that when we do random rejections, we commit some errors. And on the other hand, the inverse problem said, oh, it's okay to make an error. You're okay as soon as the error is about the noise. So we combine these two, and we can prove a couple of things. We can show that, okay, the probability that your reduced cost functions, right, compared to original cost function high-dimensional data, the probability that you are epsilon away from the original guy is actually decayed exponentially. Right? That's important. In particular, we can show that our cost function, this is the nonlinear cost function, right, is epsilon away from the original cost function with high probability. So notice that when we work at the statistical setting, we no longer have the exact thing, right? This inequality does not satisfy for all, but it's satisfied in probabilistic sense. That means, in this case, it's satisfied with high probability. And if you have 0.99%, right, 0.99 probability, then you are good, right? In particular, that is the key behind on the randomization method, why it works, right? Even though this has some failure probability, but because the successful probability is so high that you actually basically you don't see it in practice. So this one essentially is actually valid, almost everywhere in practice, right? And as you see that this is a lower bound, we can show that there's a lower bound in the produced dimensions, independent of the original data dimension, such that I'm epsilon away from the cost function. In particular, we can prove a statistical Morozov discrepancy principle. So Morozov discrepancy principle says, let me repeat, you want to solve the solutions until your error is about the noise. What we show here is that we look at the reduced data problem, right? We solve the reduced data problem, we get the solution. This is the solution for the reduced problem. But we are not interested in the reduced problem, right? We are interested in the original problem. We want to solve the solution for the original problem. And what we show that if your reduced solution satisfies the Morozov discrepancy principle, it turns out it is also a solution for the original problems, right? That's what we can show. And for linear problem, of course, we can characterize more, right? For example, the optimal cost, which is epsilon away from the optimal original one, and more importantly, the reduced solutions is actually epsilon away from the exact solutions. Let me show you a few results. Actually, I'm out of town. So what we actually, the idea is not new, right? What we actually show new is actually we prove why it works. In fact, the idea originally originated from the ExxonMobil people. They actually randomly combine the errors, the data, and they get a very good solution. And many people do, and they get a very good solution with even, the reduced dimension with 10, right? Even though the original data, million, billion, and the reduced dimension 10, it still works. Get the good solution, they don't understand why, right? Even though they make connection with the stochastic, our contribution here is actually we prove that actually it works, because if you combine the Johnson, Linda, Strauss, or random projection and Morozov, and that explains why with a small dimension it still works. So what I'm showing here, I know the blue actually doesn't look well in this classroom. So this is, remember that the epsilon, the sigma, right? The sigma, there's many choices, but what we choose is actually sparse. Right? And this is 10 sparse, 10% sparse, this is 20% and 50%. And if you think about, you have a very large dimensional, high dimensional data, sparsity projection is important, right? Because it's reduce the cost. Basically, you multiply the random with small matrix with a full vector. This is where we gain additional computational cost. So what I'm showing you is a toy problem where on the right hand side, this is the full data solution. This is the conductivity, right, with the full data. If you solve the problem with full data, this is how it looks like with 1,333 dimensions. And on the left hand side, I show you 67 sparse projections, right, with 31 reduced dimension, right, and it's 31. And you see, it doesn't look very good, even though you see a little bit here. Let's increase the dimension a little bit. If I increase the dimension to 51, you see that I only recover something about that lobe, right? If I increase to 100 dimensions, then actually basically I recover the original solutions, right? So all the magnitude is smaller than the original data, and yet we still can recover. Again, it's supported by the theories. And this is the three-dimensional problems where this is the exact with 200. Again, this is a toy problem where I have 2,474 dimensions, and this is 50 random directions projection with 67% sparsity, and you already see that we already covered these three reservoirs. But if I increase to 100, then we almost recover the original problem, right? Again, all the magnitude, but yet we can get the good solutions. And we also show that, in fact, right, I show you that there are many of them here, and you show that even 99% sparsity, right, we gain the PD solves. Right? What we show you is that not only we reduce the dimension of the data, we also gain the PD solves. That if you don't do anything, you need to 2,423 PD solve. But what we get is actually even less, right? Half of them for 2 dimension. For 3 dimension, we get it's not half, but still less. Right? Of course, this is 3-dimensional, very small problem. It's an easy problem. But the point is that we can also reduce the dimension of the number of PD solve, which is important. Okay, so let me conclude. Our group have been for the past 5 years or 10 years to work on various aspects of the inverse problems, in particular high-dimensional state, parameters, and data. What I show you actually mainly on the data, right? And this is where we can marry the classical approach, right? Inverse problem and the new machine learning type or computer science type random projection. And by combining the theory, we can show that actually it works well. Right? Even though you reduce the dimension independent of original data. Thank you.
Okay, so we have time for a few questions.
I think everybody wants to take a nap, I think.
A simple question. So you said that you have you finally do a dimension negative for your observation. So can you maybe the question is related. So can you choose some specific location of the sensor such that it can get the best results?
Oh, that's a good question. We actually don't look at that, right? So that's actually correct corresponding to the optimal experimental design, where you actually which which sensors, right, or which measurements, right, if you are given a whole bunch of measurements, which one actually the most informative, right, measurements, that's in the context of optimal experimental design, people do something similar, not what you say, right? What you say that you already have the sensor, which one is best. But in the context of optimal experimental design, you want to find the next observations, right, that you haven't done, so that you gain the most information. What we do here is actually we don't do in that directions, because we want to make a more easier way to doing things, because finding the most informative sensor is an extra layer of problem solving, right? So what we do here is very simple. We just do projections, which is in some sense is the best that you can do, without knowing where the location of the data. Just do projection, major vector product, basically, right, without solving anything. So what you said actually can be done, but I haven't done it. But I expect that you have to solve something in order to determine which one is the most sensible one. Yeah.
You said that you don't want your prior to affect the dimensions of the parameter space that the data inform, your likelihood is informed. Assuming that there is a unique peak of the log likelihood and you compute the Hessian of the log likelihood, if it is not degenerate, it will have non-zero curvature in all directions. So how do you decide which curvature is too much or which curvature is too little?
So that's a very good question, right? Even though I didn't show it here, I know why you are interested in that, right? Because you do more inverse problem. Yeah. So the idea is that we don't want what I showed you previously here. Not the data thing, right? What I showed you for two applications, in particular, the earthquake application, we actually do lower approximation first to determine the most informative direction. This one, in order to reduce the cost, lowering approximations. But the framework that I just mentioned, the new statistical way, actually don't find the where, right? That's a beauty. We don't first solve for where the most informative dimensions. The framework itself automatically detect the most informative direction, and then only put the prior. Basically, when you put the prior, right, you put everywhere because you don't know which direction, right? So the framework automatically subtract or remove the regularization of the prior on the dimension that actually informed by the data. It's only keep the one actually on the parameter space or direction that is actually not informed by the data automatically, implicitly in the formula, in the constructions, and that's I think that's the beauty. Yeah, but it's not a free lunch. I'm going to show you the standard Bayesian framework, right? You have the likelihood, you have the prior, and you have the normalized constant that you don't care, right? That's typically Bayesian. But in this framework, the denominator is actually is important, because the denominator is actually the push forward of the prior to the data, and that push forward in some sense, right, detect the dimension that actually inform by the data automatically and subtract from the prior. I can show you more detail later, but this doesn't come for free. Actually, you need to do a little bit more expensive than the usual Bayesian approach, but the beauty is that automatically does so, right, in automatic manners.
Okay, let's thank the speakers.